Good day to all of you. Today we shall discuss associative mapping, which comes under the topic cache, memory and mapping functions. Okay, in cache mapping functions, there are three functions. The first one, which I have already covered in my previous video, that is direct mapping. The second one is associative mapping and the third one is set associative mapping. In this video, we shall discuss about associative mapping. So for this, the same example which I had taken for direct mapping, I will take so that we can compare both. So example, word size, it is treated to be equal to 1 byte. Then main memory size 4 KB, 4 kilobytes. Cache size 512 bytes. Block size 4 words, that is 4 bytes. Okay, so in the figure main memory is shown here and this is cache memory. So these are blocks. This is block 0, this is block 1, block 2 till block 1023. So block 0 to block 1023 means totally 1024 blocks are there in main memory. That is taken as 1K blocks here. 1K means 1024 blocks. Why 1024 blocks are drawn here? Because they have told main memory size 4 KB, then word size 4 bytes. So total size is 4 kilobytes. Block size is 4 bytes. Then how many blocks can be made? 4 KB divided by 4B. That comes out to be 1K. That is 1024 blocks. In each block 1, 2, 3, 4 words will be there. That is 4 bytes will be there. So 1K into 4 bytes, it will be in total 4 KB main memory. Okay. And cache, here cache block 0, 1, then last one 127. So from block 0 to block 127 means totally how many blocks are there in the cache? 128. Why it is drawn like this? Cache size is 512 bytes. Block size is 4 bytes. Because block size in main memory, block size in cache will be same. Hence here in each block 4 bytes. So 512 by 4 is 128. So from here to here 128 blocks in each 1, 2, 3, 4 words. Hence 128 into 4, that will be equal to 512 bytes only. Okay, that is what is cache memory. And this figure shows the division of physical address of the word given by processor. Whenever processor requests for any word, this word or this word, it sends the physical address of the word in main memory. That we call it as main memory address. And it is divided into two parts. It was divided into three parts in direct mapping. Here in associative mapping, it is divided into two parts. One part is called as tag, another part is called as word offset. This tag part, these tag bits are used to identify which block of main memory is copied to cache block. Because suppose the word requested is in block 0, then not just one word, whole block 0 is copied to cache block. Then which block is copied? To identify that, the bits reserved are called as tag bits, right? In associative mapping, any block of main memory can be mapped onto any block of cache. So when processor asks for a word by sending physical address of the word in main memory, then the word in which memory block it is in main memory, and that block will be copied onto cache. But in which cache block it is copied, so that is calculated by some formula in a direct mapping. So cache block number is fixed where a particular main memory block is copied, but it is not fixed here. Okay, it is not fixed here. So the meaning is, if this block in main memory is copied into cache, because the word requested is in this block, then whole block is copied onto one of the cache block, and which block that is calculated by the formula in direct mapping, and this cache block number is fixed. Though other blocks were free, it would be copied here only. Okay, like that many blocks here from main memory would be mapped onto same cache block as per formula. If it is full, then it would be it would be replaced by the new data from here to here. That is, it has to be overwritten. So number of misses are more, number of overwriting is more, because many blocks in main memory as per formula were mapped onto same cache block. So direct memory mapping, though simplest, it was very easy to know the main memory block where it is copied, but there was no flexibility. It was rigid. In that memory block only, in the cache, it would be copied. But in associative mapping, with whole of the cache is available. Not just one block is fixed as per any formula. Any block from main memory, it is mapped onto cache, or from main memory it is copied in cache block. In any cache block it would be copied. So flexibility is more in associative mapping when compared to direct mapping. Next, how many blocks are here? So 1024 blocks are here. Then to represent its number, how many bits are required? So 1024 means 2 raised to 10. Hence 10 bits are required to identify any block. Block 0 means, what is the identification in binary here? 0, 0, 0, 0, 0, 0, 0, 0, 0. 10 times 0 will have to write. What is the next one here? 0, 0, 0, 9 times 0 and 1. So when we reach the last one, 1, 0, 2, 3, 1, 1, 1, 1, 1, 1, 10 times 1 we will have to write. So that gives the 10-bit identification for any block here. Okay. So whenever this block is, main memory block is copied into cache, anywhere in any block of the cache it can be copied. But which block of main memory is copied here? So to identify that main memory block number, which is called tag, that has to be stored. So here we have whenever copied tag bits. Okay. Suppose if this block is copied here, if it is free, anywhere it could be copied at that moment. If it is copied, then the tag bits associated, the block number here, 10 zeros, will be stored in tag directory. So like that, one more block when copied here, again to identify that 10 bits here. Totally how many can be copied? One after the other, 128 blocks from here, one by one when copied. With each block, how many bits will have to store? 10 bits. Where? In tag directory. Then what will be the tag directory size? Here 128, each time 10 bits to identify main memory block. So 1280 bits will be stored in the tag directory. That is what is some discussion about tag bits, which is used to identify main memory block number, which is going to be mapped onto any block of the cache, or which is going to be stored in any block of the cache. Okay, so there are 1024 blocks in main memory. In this example, 1024 can be written as 2 raised to 10. Hence, this 10 bits are required to identify main memory block. So main memory block identifying bits are also called as tag bits in the physical address of the word given by the processor. That physical address is given to identify the word which the processor is asking from the main memory. Okay, so this physical address we have written here, which comprises of two parts, tag and word offset. Okay, then these 10 bits are tag bits, which are used to identify which main memory block is going to be copied. Next we shall see what is this word offset. For that we'll have to use the data. Block size is 4 bytes. So here main memory block size and cache memory block size are equal. Whenever a block is copied from main memory to here, so 4 words will be copied. Suppose processor is asking this word. This is first word, second word, third word, fourth word. What is the numbering of this? 0. This is 1, 2, 3. So to represent 4 elements, 2 bits are required. Hence this is 0, 0, 0, 1, 1, 0, 1, 1. This we call, to identify the word in a block, that is called as word offset. To identify that 2 bits are required. Okay. So block size is 4 bytes, that is 2 raised to 2 bytes, and this is called as word offset. Hence 2 bits are required to identify any one word in a block, and that is called as word offset. The length of that is 2 bits. Okay. What is the total physical address size? That is 12 bits. This is main memory address. The tag and word offset together, what was that? Main memory address. This is also called as physical address. How many bits are there in one physical address? 12 bits. Is it correct? To verify, 2 raised to 12. It is, so 2 raised to 2, 2 raised to 10. So here, how many blocks in main memory? That is 2 raised to 10, 1024. In each how many words? So 4 words. Like this it can be divided. Okay. Or so many bytes are there. This is written as 4. This is K. So many bytes are there. This is equal to the given main memory size. Hence this 12 bits which are used to indicate one word in main memory, that is correct. So the question 1 that would be asked here, find out the physical address division. So physical address division means we have to find how many bits for tag, that is to identify main memory block, which is going to be copied in cache block, that is 10 bits. In each block, how many words are there? 4 words. To identify any one word, how many bits are required? 2 bits. So whenever processor requests for a word in main memory, it sends 12 bits address, because there are 4 kilo words are there, 4 kilobytes are there. Any 1 byte is required means it has to send 12 bits, because 4k is equal to 2 raised to 12. So 12 bit physical address it will send. Then first 10 bits will represent the main memory block number, and the last 2 bits indicate in that block which word the processor is asking for. So this is first one, that is physical address division. So another question that can be asked is tag directory size. So to find tag directory size, when main memory block is copied into cache block, which main memory block is copied into cache block identifying number, so that is called as main memory block number, or it is also called as tag. To identify any one block here, 1024 means 10 bits are required. So 10 bits form the block which is copied here from main memory. So that 10 bits will be stored in tag directory. So like that, how many blocks can be copied here? 128 blocks. Then how many tag bits will be there in the tag directory? 128 into 10, that is 1280 bits. This is the tag directory size. That was the answer for second question. What was the first question? Find the split in physical address. Then second one is find the tag directory size. Both the questions are answered. So what was the topic? Associative mapping, which comes under cache memory and mapping functions. In this, how many questions we answered? 2 questions. Find the physical address split, and second one, tag directory size. And one more thing what we learned here, associative mapping is more flexible when compared to direct mapping. Okay. That completes the discussion. I hope you understood. Thank you.